So you'll need to use the Bernoulli equation, right? So to review from last time, we derived. Well, let me explain what this problem looks like first. So this is basically an example of a flow rate measurement. If you remember the list of quiz topics, we had two of them. The last one was about flow rate measurement, and we talked about how the ancient Greeks used to put, little bumps on the bottom of rivers, and then look at how much rise the fluid had. This is more of a recent example. This is similar to what we'll talk about later today, these things called Pitot Tubes. Anyone heard about Pitot Tube? Okay. What are they?
They're used to measure like airspeed and different velocities.
Yeah, you put them on airplane wings, and they're an analog way to measure speed. But as you know, a lot of these fluid devices, they really measure forces. So basically, they use the Bernoulli equation to figure out what the speed is. And this is kind of an example of this. So you can imagine that you've got some liquid flowing through here. So I could have basically shaded this entire thing, but it would get kind of messy. But you have this liquid going through here, and it rises a little bit through here, and that's because it's got some pressure, right? If it had zero pressure and zero flow speed, there would be no rise here. The thing that's causing this is basically some pressure. And then you got a larger pressure here, because you can see the height of this manometer is different. And that's because of the way this is shaped. The fluid, even though fluid's going past both of them, here it's going past it, and here's actually impacting. And so that gives rise to what we'll call the, make sure I get it right, the stagnation point pressure. And we'll define what that is, but basically once you have a device that really goes into the middle of the flow, you generate what we call stagnation points. And that gives rise to a higher pressure here. And so the beauty of these devices is that you're supposed to be able to figure out flow rate. Remember, flow rate has units of liters per second, units of gallons per time, just as a function of how wide you make this one is. And you have a little device that tells you the height of this manometer reading. These manometer readings are supposed to be useful. They're supposed to be able to tell you like what Q is. And if you have a little graph, you should be able to match them back to back. So let's review a little bit about what we did last time, and then we'll do this problem together. Let's do it on this board. And I've got a few demos today, mostly from previous year's course projects. All right. So last time we learned that we have basically a constancy in these three pressure terms along what's called a streamline. Remember, this all equals some constant. I call it chicken. So these terms have a couple of different names. So you know this one as pressure. Hey, Blue Jeans folks, maybe I gotta mute you. Is that from this side or I think it's this side like Blue Jeans? So you know this the first term as units of well, they all have units of pressure. They all have units of force per unit area. So in terms of units, these are all force per area or energy per volume. And the latter is probably the more useful way to think about it, that there are 3 ways to quantify how much energy you have at a point. A point designates where a fluid particle is. So this first term is pressure. And they call that the static pressure. This next term is called the dynamic pressure. Remember when we did the dimensional analysis problem in the beginning of class, we talked about drag on fixed spheres. And it was basically a function of Reynolds number times a rho u squared. And that's what this is. This might also remind you of a kinetic energy per unit volume, right? Because if you multiply it by volume, you get your old friend, the kinetic energy. In fact, if you cover up this pressure term, this should be very similar to what you derived in House of Pain when you did the, projectile motion. And this one's hydrostatic pressure. I know sometimes we're not going to be using liquids. Sometimes you'll be using air. But basically, if you remember from the derivation, we basically considered this object moving. And as it moves, 3 things can happen to it. If it moves in a gravitational field, just like a projectile, it's going to decrease in speed because it's putting that kinetic energy into potential energy, or it can decrease in pressure. And so you got to keep track of those 3 things. And this says it's kind of like a conservation of energy. That says the sum of these 3 is going to be constant. There's one more Bernoulli equation which we won't be using. Let's just, I won't even bring it up. It's just, but I mentioned it last time. It would basically involved this one comes from integration along the streamline. There's another one that goes in. So all the problems I'll give you on the quiz, you'll be able to use Bernoulli's equation. We will, in about 2 chapters from now, 2 quizzes from now, we'll talk a little bit about problems that violate some of these conditions. That's where you actually have losses, things called losses, where you notice there's no viscosity in any of this. So it assumes fluids basically don't have viscosity. But there are problems that basically you can solve for this and you'll have a loss term and you'll be able to calculate the loss. And that's important if you have a pump, you want to pump something of an incline, you want to basically figure out how much jet energy your windmill's generating, etc. But for this quiz, you have these 3 assumptions. And just, and this is from integration of F equals ma along streamline. If you remember, the forces are basically pressure force and this gravitational force, and the mass times acceleration integrated becomes the 1/2 rho u squared. So how to solve problems? Last time we did this problem of, let me see if I can, it looked like this. There were basically 2 parts of the problem embedded in there because the fluid in this top portion here never leaves and in fact is stationary. So this left side of the problem, the only goal of this part was to figure out what the vapor pressure was. I think that's a little better.
Doctor Who? What is the force per area and energy per volume corresponding to?
Those correspond to all the units on the left and the units of the constants.
Oh, okay.
This is the units of this equation.
Gotcha. Thank you.
Perfect. All right, so for example, last time there were 2 parts of this problem. And this last time was about cavitation. And cavitation occurs when your pressure your lowest pressure in the system is less than what we call the vapor pressure. This vapor pressure is positive. I think you can find it from this left-hand side, and basically the vapor pressure is here, and it's clearly a negative value because it's supporting the weight of this fluid. So if we call this H, I think we called it HB last time, equals negative rho G HB, which is found just from force balance, right? The only way you can support a fluid of density rho of height h is if you applying that much negative pressure at the top. And the next part of the question was asking, where does cavitation occur? Where do we actually get negative pressure? And the answer to that was basically, if we call this z equals 0, basically anything above the line z equals 0, you're going to get negative pressure. Because you're going to have, as you see from this equation, you're going to have, this hydrostatic, basically you have this potential energy, you've got to have some pressure to compensate for it. So fluid will never leave this container unless you have basically some low pressure here. So the steps we did to solve that problem, we set up basically 3 points. And we necessarily had to set up 3 points because points 1 and 2, you had to do that to figure out what the pressure was at the cavitation points. And pressure 2 and 1 to 3, you had to figure out what the actual speed was that was exiting the container. So I think we drew this HP. We showed that this height dictated the speed that left, and that speed dictated what the pressure was there. And then we combined it all to figure out. One equation has the pressure there as a function of HP and I think the radius here. So the general thing that we use to solve problems that are open-ended like that are to write Bernoulli's equation between 2 points. So and they have to be 2 points between 2 points along a straight line. All right. So, for example, when we did between basically the water surface and the middle of the top pipe, we wrote that between points 1 and 2. Right? And like I said, you have this. It's like you're hosting a party, but then you're inviting these 6 friends. You invite the new pressure, the new velocity, and the new z. And you got to keep that in mind that you're going to invite these new terms, and you're going to have to eliminate them. All right. Now, so you should be sort of a little organized and systematic about where you want to write these. For example, you generally want to write them where you know the z values. If you don't know the z values, that's going to be another unknown. And those 2 z's are going to become 1 z because it's going to be the difference in height. Sometimes you know the velocities, but sometimes you won't. And luckily, you want to choose p so that they're at the water surface. So let me just write that down for you. So choose point 1 at the free surface, where we talked about we had balance of pressures, so that basically, so that P1 is equal to P atmospheric is equal to 0. If you've got a closed vessel, a lot of times you'll have the large container assumption. But be careful, because I've seen people abuse that in the quiz. For example, we've got a large container. and you've got these two speeds, then the velocity at the surface is going to be really small. Let's say if that's the ocean, that's the ocean, and someone just put a little stopping hole in the ocean. It'd be very low. In reality, it's of course it is non-zero, but what it does is if you keep it, it just increases all the algebra that you have to do. Such that flow rate somewhere is negligible. Negligible doesn't mean zero, it just means smaller than the other pressures and velocities. All right, the next hint. All right. So consider straight streamlines have like a radius that's infinite. So, okay, so imagine we have these problems where we have these free jets. If basically it's falling vertically, you have P equals 0 on the F side. And then the second Bernoulli's equation, rho u squared over r plus rho gc constant. If it's basically straight, then basically you've got to have pressures equal throughout. Basically, second Bernoulli's equation tells you as you go from A to B to C to D, as you go horizontally. But basically, then pressure is equal to 0 throughout the jet. I suppose you can get that from force balance too. So maybe you don't have to invoke the second one. All right, so that's pretty much what we did last time. We'll do one more closed container problem today. We'll do this problem called the clepsydra, which is these old ancient ways to measure time. But they basically, you've got to use, for example, these two tricks, especially these two tricks, to eliminate some of the unit variables. All right. So that pretty much takes care of problems that have closed containers. Now, for example, like the problem that we have today at the front, you've got a problem where you've got an immersed body in the flow. So we have to introduce this concept of stagnation. All right. So theoretically, why do we even have this concept? It has to do with the fact that you got lines of symmetry in the problem. So let's see. I think people with blue jeans can see this. Have you guys seen this before? That's how. Who has Hope Scholarship? Who has Hope Scholarship? Anyone? Does anyone have like Hope Scholarship? It's paid for by lottery, and they use these little. Don't they still use these little balls and numbers on them, and they like. I think so. Yeah. But it's all paid for by. All right. So, all right. All right. Let's see. A little higher. All right. So the reason why I can balance there is a little beyond what we're going to do right now. That has to do with the fact that it's a little bit stable. Like if it goes a little to the right, it gets pressures on the right-hand side that push it back in the middle. But one thing hopefully you can visualize from this demo is that there has to be a point where fluid makes a choice. Like basically, you all know the fluid's coming out vertically, but then as soon as it hits the ball, it's got to either go left or right. And there's a theoretical line right in the middle that it doesn't do either, and it just basically stops. And we call that stagnation point. And that is the point of the highest measurable pressure in the fluid. So if I were to, that was a ping pong ball experiment. You got hot air going to the left and the right sides, and then right in the middle, we call this the stagnation point. So I were to put pressure sensors everywhere along that ping pong ball. If you want to have the pressure sensor that blows out, you would bet on it's the one right in the front. Or I don't know, if you were sitting in like a pickup truck or something like that, where would you want to sit that you get the most forces? You definitely want to sit sort of right in the middle, in the front. So the stagnation pressure P plus 1/2 rho u squared. So basically, we've got a velocity. If the fluid has a pressure P and a velocity u, that's going to equal whatever incoming pressure I have everywhere plus the velocity squared. So it's basically saying all that kinetic energy is hitting the sphere, and it basically stops. Because like I said, some is going to go around, but some of it just has to stop. And that's basically essentially what's supporting the weight of the sphere. You have all this momentum going up, some of it's stopping, and that's actually supporting the weight. So this idea of stagnation point pressure, even though we used a solid body, it still pertains to that left-hand side problem. So here, I'll illustrate this with this. So let's do a little zoom in to that problem. All right. So even though in that ping pong ball we consider it a solid object, once the fluid is inside these sort of manometers, they're also, even though they're fluid, they're not moving anymore. So they're essentially acting like a solid. So to make this similar to that one, I'll make this height a little larger. All right. So the pressure basically right here is going to be rho g h3. That's basically supporting the weight of the fluid on top. So that's just from force balance. Okay? And the way we look at these Bernoulli equations, we kind of assume that there's no wall effect on the walls. So the pressure P3 is here, and it's also here. Basically, the pressure is constant along. Oh wait, no, that's not true. Because you have that. You have hydrostatics. But the pressure is P3 right underneath that part here. And if you got a non-zero velocity here, so we'll call that point 1, and we'll call this, so imagine this, we'll call this point 2. The velocity is non-zero here, so P comma U, but then once it hits here, that's not very clear. This velocity is 0. So it's gone from a pressure and a non-zero velocity to basically a 0 velocity, because basically right as soon as it hits it, it's like a stagnation. So velocity is 0 there. And so the pressure that you're measuring, P2 is equal to P1 plus 1/2 rho U1 squared. And that should be, so this pressure The pressure that this manometer measures, so there, I'm going to write P2 in two different ways. One through, this is from Bernoulli, and this is from force balance. We'll call this H4. So that P2 is rho G4. And the reason why it's higher is because you're not just measuring the pressure, you're also measuring the velocity. And if your fluid is moving, that's going to be necessarily a little bit higher. Okay, so hopefully you see that these two, even though they're looking very similar systems, this one, you have a stagnation point, so you have much higher pressure. And then this one, you just have fluid passing by, but it's still measuring the ambient pressure. So why don't you, I got to introduce one more idea. So what a P2 static tube is, it's a sort of device that combines both of these into one thing without taking up that much space. So basically, you've got some fluid here that just takes the fluid. Then you have a series of holes on the top and sides. So you're basically going to have fluid coming this way. Holes. And basically, you can imagine you've got a stagnation point here. So this measures P3, this measures 4. You basically have sort of manometers at both points. The middle is going to be a little higher. You have fluid that can go up into each one. So P3 is going to equal to P plus 1/2 rho U squared. P4 is equal to P1, which is atmospheric pressure. And so the velocity is going to be the difference in pressures divided by rho. So it's the same concept as you have on the left, except you put both apparatuses into one closed frame. Yeah?
I'm not sure I understand the picture.
Oh, this? Yeah. It's kind of like you have, yeah, that's not so good. It's kind of like you have a sort of a cylinder here, and the outside you have another concentric cylinder, and that concentric cylinder has holes in it. And the holes face normally upward. So basically the fluid goes in here and generates basically a stagnation pressure, and the fluid goes past the holes and also generates an ambient pressure. So it's just that basically you got, it kind of looks like a machine gun. If you've ever seen the front of a machine gun, you got the nozzle and then you got these holes on the top. These basically just allow fluid to pass by, kind of like this thing, and this allows fluid to sort of go in. There's a better one in the book. I think the book actually shows some good ones.
So there's not fluid in the and the tube with holes in it?
Each of them are manometers, so you have fluid at number 3 and number 4. But you don't have any transfer between the two. They're kind of independent. They're supposed to be independent, but you're trying to measure two independent things. All right. So why don't you try in your seat to do that problem over there? The problem that we introduced at the beginning of class.
Doctor Who.
Yeah.
For the Pitot static tube,
Yeah.
is that outer tube the essentially I guess there's fluid on both the top and the bottom of the inner tube.
Yeah, they're sort of independent tubes. It's just a way of putting this left-hand side into one container. And so each of them has a manometer at the end, but basically one of them takes in fluid directly, the other one allows fluid to graze past it.
Okay.
There's a better picture in the book. And I think if you just Google it, I'm sure Wikipedia has a nice video. So I'll give you a little hint with this one. Sometimes you have to draw new variables. So I'll give you a hint. You need to basically label this. It's not given, but you're going to have to introduce it, and then you have to get rid of it. Now let me show the genes world what that looks like. The blue genes, folks, you have to introduce a new variable, x, that you're going to have to get rid of later. Because remember, Bernoulli's equation works along a streamline. So you have to consider the middle line that goes through, actually passes through here, influencing this pressure here, and then is measured to the right. I got to get one more. I forgot to do. We'll call this D1. So you have basically so I'd first start by labeling 2 points in the fluid. And they should be along a streamline. So basically, only a streamline that intersects with this point is going to be over here. So I'll tell you what, you're going to do that and that. And then write Bernoulli's equation between there. And then you're going to have to use one more equation to figure out what the pressures are. I give a hint. You basically want to put it along the middle of the tube. That's the only place that you'll have some idea of how the pressure and velocity behave. So a hint, I would choose the 2 points for Bernoulli's equation right in the middle of the tube where I labeled them, because that's along a streamline, and that's when you'll know what the velocity is going to behave. Pressure for one. Good. Yeah, because it's a stagnation point. I think so. No, not the pressure. The velocity is 0. The pressure is measured by the height of that thing. Well, you know h, and you're going to label it x. So you have to write it in terms of that, and then hopefully you'll get rid of the x's. So in general, when you do these problems, you're going to have to use three things. Bernoulli's equation, you'll have to use Bernoulli, because Bernoulli is the only way you'll introduce all three things together: pressure, velocity, and position. Maybe you have to use a force balance, because that's the only way you're going to relate points that are not along a streamline. Relate points not on a streamline. For example, the points inside these tubes, they're static, so they're not along any one streamline. And the last thing you're going to need to use is conservation of mass. So each of them has their own particular tools of mass. Like I said, Bernoulli relates P, U, and Z. Force balance will relate geometry and some pressures. And conservation of mass tells you that the fluid coming in through this big part is going to equal the fluid coming out of the small part. So we showed last time that that was equivalent to U1 D1 squared equals to U2. Right? You almost always have to use all three tools in every problem, because otherwise you're not going to be able to, you just won't have enough tools to solve for it. So if you guys are stuck, you can just rate. If you're in the blue jeans world, you're stuck, you can just ask a question. Raise your hand if you're done. Anyone done? All right. Okay, so again, you want to think of the 2 points, and like I said, the best choice is really where you know the most about this fluid. And you know the velocity is going to be 0 there, because that's a stagnation point. So you're going to have U2s there. And eventually you're going to figure out what the pressure at P2 is due to the height in that fluid, height in that thing. Similarly with the pressure in P1, it's going to be H plus X. Right? So you're going to do the Bernoulli's points between those 2 points. So we got P1 plus 1/2 rho U1 squared plus rho G Z1 is equal to P2 plus 1/2 rho U2 squared plus rho G Z2. The other nice thing about choosing it horizontally is that you know for sure that the z's are equal, because it's not going up or down. Just like a ball is not going to change in speed unless it goes up without drag. You know U2 is 0 because of stagnation point. That is what this sort of L-shaped pipe does. Not every point that touches that pipe is going to be 0, but definitely the one in the middle. And that's the theoretical point that you care about. And now you have P1 is equal to rho G H plus X. Oh, no, just X, sorry. So that's Bernoulli, and then force balance. P1 is equal to rho G X. P2 is equal to rho G H plus X. And then you just substitute it in, and you'll solve for U1. So let's see, we substitute in, and then we're good. Let's do it on the next board. Oh, maybe you don't even need conservation mass for this one. Rho gx, no, rho gx plus 1/2 rho U1 squared. I guess you do, because they want the answer in flow rate. So figuring out the flow rate is the same as figuring out the velocity. Equal to rho G H plus X. you get u1 squared is equal to 2gh, u1 equals to square root of 2gh, q is equal to pi d1 squared over 4 times this is the speed times the area. Speed times the area of the pipe. So hopefully you'll see that this quiz 3 is actually not going to be a lot of writing. There's a problem I can show you that you have to do integration, but there's only basically when you look at emptying containers of fixed height, then you have to integrate because the height of the container will dictate the speed that it comes out. But for problems like this, a lot of it is just being very careful about choosing the points 1 and 2. Questions on this problem? Yeah?
Why is D2 important? I mean, I can see that it goes into a funnel point at D2, but we don't seem to care about that.
Yeah. So what that so the question is, this problem didn't seem to use D2, and what that means is that physically D2 doesn't influence the answer. The D2 can be could change, could be up or down or whatever, and it doesn't actually affect what goes on at the stagnation point. Physically, I think that breaks down when D2 gets really small, but if you think physically, what's going on? I'll draw it on board 1. Like if I were to draw all the fluid streamlines, basically where are all the fluids going? Like basically the top one's got to go here, bottom one's going to go here, and here. So you get basically this contraction that U2 is equal to, let's see, U2 is a U1 times D1 squared over D2 squared. And because D2 is smaller than D1, you get a U2 increase in speed. That happens everywhere, but the stagnation point, it doesn't affect it because it's always hitting the pipe. So it doesn't actually influence the problem.
It would if we were trying to find like U2 at the end of this.
Yeah. For example, there's another problem in the book. There's many variations of this problem that I think are good to practice. For example, there's a variation of this problem that looks like this. I can't remember what the fluid height looks like here, so I'm going to just draw it over. But that doesn't have a static tube. It doesn't have a stagnation point. It just has fluid that basically goes past here. And then you're supposed to figure out this height h. So let me think carefully. So the velocity increases. So I think you should actually have a lower height. The velocity increases, so the pressure. The velocity increases, the pressure should decrease. So I think it should go like this. That's what I don't remember. It's in the book. But here, for example, definitely you need D1 and D2. Does that seem right? Do you think the fluid here should go down or up? I think it should go down, right? Like this. And that's some very strange and surprising things about fluid pressure. Like basically, you increase in velocity, the pressure goes down, and that's what Bernoulli's equation tells you. That basically, if you got an increase in speed because of the contraction, the pressure will go down. All right. So this is, let's see, blue jeans people, they can see this. All right. If I blow through this, do you think the things will come together or apart or stay the same? Who thinks it's going to come apart? Because like the fluid's like pushing it all out. Who thinks it's going to come apart? Who thinks it's going to come together? Why?
Pressure.
Why does the pressure decrease? Yeah, because the velocity is going up. The velocity was 0 and it's going up. So you guys basically think, I can pull this thing together if I just blow? All right. Another COVID-safe demo. pretty cool, right? I'll do one more time. Okay, you guys will try it too. I guess it's going to get pretty dirty by the time you get to the end, but yeah, if you don't want to do it, you don't have to do it. But you can do it. You can try it if you want. Oh, by the way, see that thing that says quant in that back wall? That's the thing that's been measuring the particle count throughout the whole classroom. At some point, we're supposed to go do experiments and go like stand there and just spit on it or something. But it records temperature, CO2, all of this other stuff. Okay. Okay, I want to draw one more thing on the board, the clepsydra problem. And we'll end with a demo. All right, let's do this next problem, clepsydra. And I also have one last demo to show you. I think that demo works pretty well. It's actually it's still sometimes like the intuition. We sometimes get it wrong, but that's pretty nice. That was made at Invention Studio. All right. So these examples here, they could have been liquid or gas. Anything that you can sort of increase in speed. I would say one of the first applications of Bernoulli's equation back in the day, like before digital stuff, was these, what they call water clocks. All right, let me see if I can get this spelling right. All right, so this is a problem 3.94 in the book. The clepsydra. Greek? Oh, I don't know what is. Does anyone know what that means in Greek? Okay, I think it means water clock. That's what I'm guessing, because that's what it does. There's the claw sounds for. I know there's like all the some of the STDs are like from there's chlamydia. I don't think clepsydra has any. All right, so this is what they did back in the day. They basically had these huge vessels, like pottery-made vessels, and they didn't have digital stuff, and they wanted to know what time it was without, depending on the sun, because sometimes it's cloudy. So the best they had was basically looking at how quickly containers drain, because it takes time for containers to drain. And what they discovered was that basically, if they made the vessel a certain shape, so, for example, that water bottle on the table, what's your name? Dustin's water bottle. Like, if you turn it empty, turn it over. If you turn it over, the speed, do you think it's going to be highest in the beginning or the end? The beginning, why? Yeah, because you have all this hydrostatic pressure. Just like those manometer problems, you have all this hydrostatic pressure. I always forget if I'm on screen for the Is it leaking? All right. Oh! But you have all that hydrostatic pressure, and the issue is when the speed's really high, the flow comes out a lot faster. So in the end, it kind of dribbles out. So basically, it wouldn't be a very accurate time measuring device if you were trying to put little markers along the top, because it would progress non-linearly. So the ancient Greeks, what they figured out, well, if I change the area, the cross-sectional area of the container, I can make it so that it proceeds linearly. And then I can actually say, hey, it's 3 o'clock, it's 4 o'clock, it's time to feed the goats. So question, what is R of z given R2? So we'll call this basically the radius at the end R2. Given R2, and let's say we want it so that, and we want dz dt, so we'll call this the height. Z. We want the height of that thing to go constant. And we want something reasonable like 1 centimeter per hour. so that, I can actually look at it and 24 hours will fit into my house. All right, see if you can give it a shot. I'll just draw the stuff that comes out. And you're free to talk to the person next to you. I didn't do a good job of encouraging people to, at least people are working together for the course projects, but for the quizzes I noticed that most people are actually like in total isolation and not like talking to any other human beings. So I put that little quiz thing to try to encourage you to like find someone, a friend or someone to talk to about these problems. There's some study groups, but I wish there were more. So you got to choose, like the previous problem, label 2 points to apply Bernoulli's equation, and then use appropriate assumptions, conservation of mass, etc. People do the homework the day before the quiz or over the weekend? Over the weekend. Okay. Camduck's going to teach on Monday, so maybe Camduck you can go over the homework problems. But if people have issues, maybe email me over the weekend and I'll send it to him. What about P1? Atmosphere. What about P2? So we can choose P2 to be right when it exits the container. So then it could also be 0, too. You're right, you could choose it right before it exits, or you can choose right after. But right after, it's in a jet, so it's going to be 0 pressure. Oh, that's what that looks like, huh? So seldom. Yeah, a lot of ancient cultures had them. That would be a pretty decent course project, actually. What I really want is a clepsydra that measures the time of one semester. So I could start at the beginning of the semester and it would just end. You have to make it out of like viscous fluid. Good. Then, except the negative sign, probably not. So I would just label, you can call that z equals 0, and then, or you can call this z equals 0 and that equals z. But I'll make sure you just label things correctly. So if you get Bernoulli, you got to apply conservation of mass. And remember, R2 is given. And then you want the equation for R as a function of z. And you got to use these tricks. For example, the large container thing. All right. I want to show one more demo, and maybe we can start with one of the last problems. Okay, so definitely, I think most people labeled point 1 as the water surface because you know a couple of things there. P1 is going to be atmospheric, it's going to be 0. And also because it's a large container, you're going to assume that the velocity is very, very small. Physically, like we know that velocity is going to be, is not here, it tells us it's non-zero. It's 1 centimeter per hour. But hopefully it's coming out here at like 10 centimeters, like 100 centimeters per hour. So that hopefully that it's negligible. So I think everyone knows where to make the first point. Now the second point is subtle. What's your name again?
Alex.
Alex. So Alex put it here, which is a good choice, but there's a slightly better choice. Because here the problem is the pressure is given by the height of this thing. You want to put it in a place where you definitely know the pressure, and you want it to be hopefully just 0. Because this year the height of this thing is going to change. So theoretically, you basically want to put the point right in the external jet. This is the funny thing about fluids. It's got basically, non-zero velocity, non-zero pressure. Then as soon as it exits that hole, as soon as that water molecule exits the hole, it has the same velocity, but the pressure is 0. So, because it's basically in the atmosphere. So P2 is 0, and U2 is non-zero, because that's what we're trying to figure out. The other thing is, I'll try to be consistent with how you label these things. So if we call that Z, the best way is to call this Z equals 0 here, and this is Z is equal to Z. That's not the greatest notation. I guess we call it H. That's probably better, and then we'll replace it later. But certainly got to make clear that Z2 is at a lower height than Z1. If you don't do that, you're going to start getting negatives, and they're going to get worse. So P1 plus 1/2 rho U1 squared plus rho G Z1 is equal to P2 plus 1/2 U2 squared plus rho G Z2. So what you have left is Z1 minus Z2, which is, so let's not skip steps. I'll be rho G Z1 minus Z2 equal to 1/2 rho U2 squared. Z1 minus Z2 is H minus 0, so we got ZH is equal to 1/2 rho U2 squared. So we made some progress. We've shown that, like the siphon problem, the speed of exiting the stuff is dictated purely by the height. I forgot one of the rows. All right. But that doesn't tell us what R of Z is. That comes from conservation of mass. So conservation of mass. So this is interesting because you assuming U1 is much, much smaller than U2. And now conservation, you have to assume that it's non-zero. So you got U1 R of H squared is equal to U2 R2 squared. You got U2. The easiest way to do this is now we substitute. So first we know we know that's equal to a constant, so we'll assume this is C U1, and we substitute for R2 for U2. We've got C R squared as a function of H is equal to plug this in. So let's make this nice. U2 is equal to square root of 2GH. Square root of 2GH times R2 squared. So R squared equal to 1 over C 2GH to the 1/4 R. So that's how you basically want to make a container as a function of height. So in other words, it kind of looks like a parabola. For a small h, R is constantly increasing, but it increases really slowly with height. So it's a kind of a little bit of trick because you have to assume that U1's small for one of them, and the other one you can't ignore it because you definitely need it for conservation.
Doctor Who?
Yeah.
I don't understand why you can just say r squared, because isn't that it should be rho v times an area, so shouldn't you do the area of a circle with the diameter of r sub 2?
I guess I shouldn't skip steps, but the conservation of mass, the pi's cancel, so it's Q1 is equal to Q2, and you're right, that's U1 pi R1 squared equals to U2 pi R2 squared, right? So the pi's cancel.
Oh, gotcha. Okay.
So again, it's just two steps, and you need both of these. You need Bernoulli's equation to tell you how fast the fluid is going, and you need conservation of mass to dictate how fast one fluid is from one location to another. So the last problem, I'll just draw on the board, and I gave this on a previous quiz a few years ago.
Doctor Who, can you move the camera for blue jeans?
Yeah. Faucet. So as you know from the kitchen faucet, your fluid doesn't come out in a cylinder. It starts as a cylinder, but it goes down to a point. It sort of narrows. Can anyone physically say why? Walk through why it's sort of narrowing? You've seen it narrow, right? Yeah.
Because since it's
well, atmospheric pressure is acting everywhere. I think there are definitely problems for which atmospheric pressure is important. For example, suction cups. You put a suction cup on the wall. If you don't have atmospheric pressure, you won't have any forces. But this, for example, if you were doing the same experiment in Colorado or at sea level, you would get the same reduction in air. So the pressure is acting everywhere. It's not able to sort of act more later. Yeah.
Didn't you say?
Would it have to do with the fact that, since the water particles are acting as basically free particles, they're being acted on by gravity, accelerating?
Yeah.
So their velocity is increasing because of conservation of mass, the diameter of cross-section.
Yeah, that's exactly right. The key word is acceleration. Just like a ball falling will accelerate and increase in speed. But fluid is funny, it's cohesive. So when it increases in speed, it's got to decrease in area, so it basically maintains the same flow rate. And so that's physically, hopefully out of the course you get the math out of it too, where basically you're supposed to crank out. But you got to understand physically what's going on, because otherwise it'll be much harder to solve these problems. So what is R as a function of Z? So again, you have R as a function of Z here, R as a function of Z out here. And you have gravity, and we'll call this Z equals 0. The easiest thing, we'll call this Z is equal to negative H. But you basically want to solve for the shape when you have a gravitational. This is a pretty heavy lecture, so I don't think we're going to finish it. But I do want to show this one last step. Well, I gave that on a previous quiz, so we can talk about it this time. All right, so this nice little baby, every time I walk through cams with this, people kind of give a look. Does anyone know what this is? What? What you said, potato gun? Yeah, potato gun. They're actually pretty cool. So This works also with Bernoulli's principle. Basically, I'm going to take this bike pump. They said it can only take like one squeeze, so I got to be really careful because it's just handmade. So I'm going to put this in. First, I make, and there's a little valve here. They only take one, but let's give it 5 just for fun. It should be fine, right? I'm just waiting for this thing to explode into shards in my face. Okay. We'll take this off. And I got to put a proper projectile in there. I'll put this dirty random Kleenex in my pocket. And then, where's the Blue Jeans camera? Oh, it doesn't go that far. How does this work again? Okay, so. Whoa! But they made this last year, and they gave it two fittings. One with a potato fitting, but I haven't put that on because they said it actually goes really far. Potato gun. But so in terms of energy, basically you have this. Basically, I've taken all this stored energy from my arm and put it in here. So this is all like high pressure. From what I read here, it was like 20 kilopascals, and then you just put an object in. So let's put another random dirty tissue. I actually really want, at some point, someone should do a course project with like ancient weapons, because that's how there's like blow darts. People actually use their own breath to actually shoot things. It's pretty amazing. It's so satisfying. Okay, but I'll leave this in the back if people want to play with it before. If I get a real projectile, I think I could really get it to hit the wall. But that would probably this probably has already been pretty disruptive to the other class. So I like that course project because it actually works, and I think it's pretty cool to destroy things once in a while. All right, 9/11. I'll give a few more. So R naught. So you're given R naught and U naught, and you solve for the radius as a function of c. So conservation of mass. So we'll call this point 0, and we'll call this point 1. Okay. So Q naught is equal to Q1, and you'll need that because R1 is equal to all right. The next thing is a free jet everywhere, so you're going to have the pressures are all going to disappear uniformly. But very similar to the last one. The velocity later is whatever the initial velocity is plus whatever extra acceleration you've gotten from falling in height. And I should have made this more clean. And so putting this all together, so we basically have these two facts, and you just have to put them together. So we'll just substitute up here. So we substitute here, R naught, U naught over U naught squared plus. All right, and that's as much I'll simplify for you. Yeah, and that's the end of class, so you guys can come up and play with the demos and stuff. they're pretty heavy, so it's a good chance to play with them before.
Last example.
Yeah.
Between z equals 0 and z equals negative h, what is that symbol